Ours is a small but fertile planet. It's a generous planet. It's always given us what we need to survive and grow. Today, there are nearly 8 billion people in the world, and we still dream of abundance. Our use of digital and green technologies has skyrocketed. As a result, we devour gigantic quantities of metals. But what if we've gone too far in our exploitation of the Earth? In the 21st century, scarcity is threatening. Perhaps it's time to seek our metals elsewhere.
We are the first generation that can look at the planets and can look at the stars and say, we can go there, we can do that. We can touch the stars, we can touch the planets.
Mitch Hunter-Scullion is just 23 years old. After excelling in his studies of international trade, he founded the Asteroid Mining Corporation in the British city of Liverpool. It's far from being a multinational corporation. He has a few colleagues across Europe. They only rent office space when they need it. What Mitch Hunter-Scullion is selling is an idea.
We are on a planet which is 36,000 kilometres in diameter, and we are in a position whereby those resources with a growing population are rapidly depleting. The inner solar system can provide all the resources that our society needs to grow exponentially for at least 100 years. Yeah, so there are you can find almost every resource you can find on Earth on an asteroid, just in varying quantities. To give you some approximate figures, all the mines on Earth currently mine 200 tons of platinum. On a single 1 kilometre diameter asteroid of a metallic composition, we can reasonably expect to find at least 100,000 tonnes of platinum per asteroid. So you're in a position where one asteroid can provide more platinum and gold than every mine in human history combined.
Deep Space Industries.
Mitch Hunter-Scullion isn't the first to bet on the idea of space resources. Nearly a decade ago, Deep Space Industries and Planetary Resources appeared on the scene to great PR fanfare.
Ladies and gentlemen, Dr. Peter Diamandis.
Seattle, April 2012.
The vision of Planetary Resources is to make the resources of space available to humanity both in space and here on Earth. The Earth is feeling a resource pinch. And ultimately, we have the ability to turn that which is scarce into abundant. And so now is the time that we need it most.
Both US companies were created thanks to major private funding.
Eric Anderson.
We also have been fortunate enough to include in our company two of the key people at Google. So we have Larry Page from Google, Eric Schmidt from Google.
This is smart money investing in one of the largest commercial opportunities ever, going to space to gain resources for the benefit of humanity.
These new players flaunted their finances and their ambitions, and that was enough to get the blogosphere excited about their potential. In the history of astronomy, the existence of asteroids was unknown until recently. Yet, without realizing it, we've always encountered them, thanks to the fragments that fall to Earth as meteorites.
When you look at the sky, you don't see rocks. Getting used to the idea that rocks could fall from the sky took until the late 18th century.
Mathieu Gunel is a professor at the National Museum of Natural History in Paris. He's responsible for the meteorite collection.
All through the 17th and 18th centuries, there was an idea that meteorites might be thunderstones or lightning stones. There were some scholars who could conceive of rocks falling from the heavens, but they couldn't think of anything beyond the atmosphere.
In 1794, German mathematician Ernst Chladni was the first to propose that their origin was outside the atmosphere. Little by little, the entire scientific community accepted the idea that meteorites come from bodies of rock traveling through the solar system. In 1801, Italian astronomer Giuseppe Piazzi mapped the stars. On January 24th, he detected the shadow of a planet his calculations told him should exist between Mars and Jupiter. In fact, he had just discovered Ceres, the largest asteroid in our solar system. Other discoveries followed: Pallas, Juno, Vesta. In 1868, 100 objects were detected. Today, we've counted nearly 1 million asteroids, which orbit between Mars and Jupiter in the so-called asteroid belt.
If I were Han Solo of Star Wars, I could cross the asteroid belt with my eyes closed. The asteroids are numerous, but small in an infinitely large space, so the probability of encountering one is still very low.
Patrick Michel is an astrophysicist at the Nice Observatory. He's an asteroid specialist who's taken part in the largest solar system exploration missions of NASA and other big space agencies. In 2012, Planetary Resources asked him to join their team of top flight consultants.
Asteroids contain resources similar to what's found on Earth because they're the remains of the building blocks which formed the Earth and other planets. In the beginning, 4.5 or 6 or 7 billion years ago, our solar system was a disk of gas and dust encircling the Sun. Then this dust began to come together into clumps, some of which ended up as planets. But part of this material never managed to form a planet and ended up between Mars and Jupiter in the asteroid belt.
It is probably the case that nearby Jupiter, with its gravitational force, prevented these asteroids from gathering. In other words, every time these asteroids tried to unite, Jupiter's gravitation would disperse them again.
Far from Jupiter's influence, billions of asteroids did manage to collect. Little by little, they formed the Earth. As it grew, its composition changed.
All celestial bodies, asteroids and planets alike, are hot inside because of radioactive decay. When the temperature rises, they melt. And when a body made up of rock and metal melts, the denser metal tends to be found at the center of the body, while the rocks are found on the outside.
When Earth was formed, iron pulled out all the elements which tend to bond with iron. Gold and platinum, for example. So all the precious elements went into the core. What remains in the mantle comes from impacts that took place after Earth formed. We call that late heavy bombardment. The abundance of rare metals we have in the mantle can only be explained by the collision of asteroids. When you wear a piece of jewelry, much of what you have comes from celestial matter, the asteroids.
In that case, the riches of the Earth's crust are only a tiny fraction of what's in the asteroid belt. After studying the characteristics of meteorites that came from there, we can sort asteroids into 3 main types.
S-type objects are mostly silicates, rich in rocky material, heat-resistant, and formed near the Sun. C-type are carbon-type asteroids, rich in water. They're formed beyond Jupiter, where water can condense. Then there's a kind that contains metallic objects, M-type, M for metal.
These are also the rarest type. One of them is Psyche, a metallic mammoth more than 200 kilometers in diameter. It's a product of the solar system's intense phases of formation. Many planetary embryos have formed. But unlike Earth, these massive bodies with iron cores never reached a sufficient size to withstand collisions. According to space miners, fragments of these metal cores would contain much higher proportions of rare metals than those found on Earth. They travel through space more than 250 million kilometers away. They can't be accessed without the help of celestial mechanics.
Between Mars and Jupiter, there are unstable regions in which celestial bodies orbit the Sun on a lengthening trajectory. That lengthening can reduce the minimum distance from the Sun and make them intersect with Earth's trajectory. In terms of the thrust needed to reach them from Earth, some of them are more accessible than the Moon.
These asteroids that sometimes pass very close to our planet are known as near-Earth objects. There are more than 20,000 of them, and they are the main targets of space miners.
Asteroid Mining Corporation is developing a roadmap to the utilisation of space resources. We're looking to prospect, explore and extract materials from asteroids. Our first project is to essentially create a database of 50,000 asteroids.
This type of database already exists. The most famous one is Asterank. The numbers found there can make the head spin. But for the most part, they're merely estimations based on the type and size of the asteroids observed. To accurately assess the solar system's resources, space miners are developing their own observation methods. To achieve this, Mitch Hunter-Scullion is working with John Moores University in Liverpool. Professor Ian Steele is an astronomer who specialises in studying meteorites using spectroscopy.
Spectroscopy is simply the process of splitting light into its colours. It takes the light, and rather than passing it through a drop of water like we have in a rainbow, we pass it through a piece of glass. So either a prism or a grating, which has lots of lines ruled on it, and that does the same action. It splits the light into its different colours so we can observe it. If we just look at something like the Sun, that has all the colours of the rainbow in it, because the Sun is made of lots of different gases. If we look at the spectrum of a single element, like neon or argon, then we just get a few different colours. We get like a fingerprint of patterns of different wavelengths of light, different colours of light, which is unique to that element. Spectroscopy, in theory, can determine any element, because all the elements have their own different chemical signatures and all their own different patterns of light. Asteroids are a long way away in space, so obviously we can't sample them directly. So instead we have to look at the light of the bits of asteroid, which we call meteorites, that have fallen to the ground on Earth.
Professor Steele compares the light spectrum of the meteorites with that of the asteroids he observes from Earth and combines the two. He's then able to estimate the composition of each asteroid. But the observation process from Earth is not easy.
The light from them is very faint. We need the biggest telescope to observe them to collect as much light as possible, and that makes it more precise, but it will still never be as good as we can record here on the laboratory on the Earth. Around the Earth, we obviously have no atmosphere around us, so there's nothing blocking the different wavelengths of light, so we can make a more fine discrimination between different types of asteroids. Because remember, what we're trying to do here is not necessarily just find asteroids that have iron in them, we want to find asteroids that have platinum group and rare earth metals. The signatures are much more subtle. So the challenge with the project we want to do with AMC is taking the spectrographs that we've built for telescopes on the Earth. So we operate a telescope out in La Palma, a big 2-metre telescope that weighs 20 tonnes and has a spectrograph on it that weighs 10 kilograms. What we've got to do is try and miniaturise that down into something that will fit in a CubeSat that's only the size of a cereal packet and must only weigh a few kilograms.
I'm ready. I'm also ready. Wait a minute. Let me readjust GoPro.
CubeSat is a new standard of miniature satellites based on 10 by 10 centimetre modules that can be assembled together. Their components are inexpensive. Another advantage is that their small size means they can be cheaply deployed. They can even be launched by hand.
We're very fortunate to be millennials, where we live in a society where you can gain access to satellite technology at a very, very low cost, comparatively speaking, to the space missions that went before us. So, for example, our asteroid prospecting satellite 1 has a budget of €7.2 million, which is dramatically lower than any space industry would do.
4, 3, 2, 1, 0, +1, +2, +3, +4.
In 2018, an Indian launcher put about 100 CubeSats into orbit. Among them was Archids-6, the first prospecting satellite from Planetary Resources. It marked a milestone in the mapping of space resources. But it also had to turn its hyper-accurate sensors towards Earth, collecting conventional imaging data that could then be sold. An important way to make some quick money. Because, like all space mining firms, Planetary Resources had barely any income.
There are arguably many challenges to be said. We are talking about a 10, 15, 20-year development cycle to see the industry to maturity. Our first phase, our prospecting phase, is the most economically important for us, purely because if you want to develop an asteroid mining industry, you have to be able to sustain yourself through the development of that technology. And to do that, you need to be able to provide an economic incentive. Our business model is based upon the metallic asteroids, which compose about 4% of all total asteroids in the solar system. They're the ones which we are most interested in from an economic perspective. So they're the ones that we would restrict supply of to our own primary customer segment. And if customers wanted to gain access to those data points, they would have to pay a huge premium to gain access to that information. We are essentially creating a market for space resources on Earth currently.
3, 4.
Not all space miners have the same business plan. For Planetary Resources and Deep Space Industries, one resource was considered perhaps even more valuable than platinum or rare metals.
First is water. Okay, so water in space, as you will come to learn, is perhaps the most valuable of the materials that we will use and find in space. Obviously, it's something that's critical to our life on Earth, and of course it would be critical to our life in space. But what we also need to realize is that water and its constituent elements, hydrogen and oxygen, are the most efficient forms of rocket propellant. As if we're able to successfully deploy and mine for water, we're going to create a network of propellant depots, of gas stations that literally open up the roadways to the rest of the solar system. So it's going to drastically reduce the cost of deep space exploration.
In 2016, Deep Space Industries developed Comet, a water-based space thruster. The water could be extracted directly from carbon-rich asteroids. It's easy to imagine swarms of probes on their way to the rich mining fields in the asteroid belt. On the way, they'd need to fill up at these space gas stations.
What's fascinating about new technologies is the promise of a new reality, even if it's still only virtual.
Jacques Arnaud has a PhD in the history of science. For 20 years, he's held a position that doesn't exist anywhere else. He's in charge of ethics at the French National Centre for Space Studies.
Nature
Nature has given humans something a little strange, called imagination. It's the capacity to project ourselves into another spatial or temporal place. And there's curiosity, which we share with other so-called higher animals. When you combine curiosity and imagination, You've explained a big part of our drive to explore. For tens of thousands of years, humans have crossed mountains and seas. We've flown through the air. Now we're traveling through space. As long as we want to remain human, we'll have to deal with this fascination. We'll also have to reckon with our ability to invent the things that allow us to go and explore beyond those mountains and seas. Since the beginning of the 1960s, space has been seen as the new frontier, something unknown that we have to go and explore. The new space concept of commercialization takes up this idea and gives it a new face, new profits, a new technological appearance. Rockets that can return to land on their launch pads have become an almost mythical image. We're finding ourselves in a retelling of a mythology, but it should be seen as a story that's yet to be written. Instead of just waiting for the years to come, 2020, 2030, 2040, we should be aspiring to build this future ourselves. And it won't be the future, but simply a slightly different present.
Reinventing the present requires a good business plan, and space miners have to keep their focus firmly in the here and now. They must convince investors with the prospect of new business opportunities in space.
It's totally self-funded AMC through my inheritance. We had small amounts of money from the Scottish Government and a small amount of money from the UK government. So we need to raise 7.2 million euros over the next 6 months in order to then move on to the manufacturing of the satellite. We will be maintaining that presence within Scotland, but also adding to that by being in Luxembourg. So it's basically joining two dots together to make a straight line.
This is Luxembourg, a tiny nation where finance is big business. It's forever reinventing itself economically. Today, the country's betting on the resources of the future.
It's no longer science fiction. We're rapidly nearing the day when we'll use the first space resources.
Marc Serre is the first president of the newly created Luxembourg Space Agency.
What we mean by space resources are the materials found on celestial bodies, like the Moon, asteroids, Mars, or other objects in the future. If a company wants to develop a new product or service, they can come to us. If their goals are in line with the way we want to develop the sector here in Luxembourg, that opens the door to possible support. The company's activities have to remain sustainable and serve the development of all humanity.
In 2016, Luxembourg's government invested 25 million euros into planetary resources. Similar startups, including deep space industries, have also set up here. Today, Mitch Hunter-Scullion has come to pitch his Asteroid Mining Corporation project to the LSA. Business is business, and the meeting is confidential. The stakes are high for space miners because they're looking for much more than money. The big issue is the right to exploit the resources of space.
Today, all space activities are governed by international treaties. Unfortunately, the treaties are not specific enough regarding what can or can't be done with resources found in space.
Since the 1967 Outer Space Treaty, space has been considered common territory for humanity. Nations couldn't appropriate its resources. In 2015, the United States changed that, passing a law intended to boost the competitiveness of its private space sector. The law allows American citizens to appropriate resources in space. In 2017, Luxembourg passed a similar law for companies based in its territory.
We wanted to be flexible, but also to leave the door open. In hindsight, there are obviously questions about conflicting activities and the available surface space on a celestial body. These are questions that I hope will be discussed and resolved at the international level.
Following the United States and Luxembourg, many countries are interested in space resources, including China, which has big plans when it comes to development in space. A new international treaty is being devised, which will try to harmonise the different players' ambitions. It might be called upon much sooner than expected because the big space agencies are embarking on Phase 2 of planned space mining, exploration and prospecting.
9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
We're currently living in an extraordinary era for asteroids because there are currently 2 space missions to reach asteroids. NASA's OSIRIS-REx mission and the Japanese agency JAXA's Hayabusa 2. Asteroids interest very diverse groups with very different goals. But right now, they all need to know the same things: what they are made of, how are they made up, and what's their internal structure. OSIRIS-REx is an acronym. One of the S's stands for security, one of the R's for resources. Because even if it's primarily a scientific mission, the information it brings back will of course help miners and those working in security.
Just like Patrick Michel in Nice, scientists here in Meudon, in the south of Paris, are contributing to these 2 international missions.
We must use all means to advance technology and science.
Maria Antonella Barucci is an astrophysicist and planetologist. She studies the chemical and physical nature of objects in the solar system.
Exploration of asteroids for what's being called mining is increasingly interesting. But before actually mining, it's necessary to understand the composition and the mineralogy of these objects. You have to go there, take samples, and bring them back to Earth.
That's the process the space miners' probes will go through in their exploration phases.
It's essential to have a navigation camera that will give us images and help us to calculate an initial model of the object.
The OSIRIS-REx mission is orbiting around the Bennu asteroid, and the main goal is to survey the object. Thanks to the camera, we can get a full characterization of the surface. There are rocks, different textures, structures, craters. We'll select several sites where landing poses no risk. The probe won't actually land. It just touches the asteroid with its arm. We call this touch and go. It touches, gets samples, and leaves again. The arm uses nitrogen. It pushes along the surface to stir up the regolith, which is then sucked up.
Regolith is the thin layer of dust and rocks on the surface of the asteroid. In 2019, the Hayabusa 2 probe sent images of its 2 successful touch-and-go efforts on the Ryugu asteroid. In 2020, OSIRIS-REx did the same from the Bennu asteroid. When both probes are back on Earth in 2023, scientists hope to have just a few hundred grams of samples.
These samples can be studied for years and years. More than 50% will be put aside, so future generations can study them with more advanced instruments.
These missions are technological feats. But the space mining exploration phase has to be even more accurate in its surveying of asteroids. The miners have to go further, or rather deeper.
A touch-and-go mission is not going to allow you the confidence that the resources that you're looking for are within that asteroid. You have to land on the asteroid and you have to be able to take a core sample. By being able to dig into the surface of an asteroid, it basically confirms to us that the material within the asteroid is the same material which is on the surface. And that essentially validates our entire business model, that it's economically viable to go and recover material from that asteroid. The asteroid exploration probe will take a small core sample, so it's not going to be a large core sample, but it will essentially be a miniaturized version of our exploitation missions. We are going to be using space drilling technology, which already exists in a prototype phase.
This drill was developed for sampling on Mars, then adapted for drilling in Antarctica. It needs little energy and exerts little pressure on the drilling surface. That could make it the ideal tool for drilling in low gravity.
We are going to expand upon that technology with our partners at the University of Glasgow to get that into a position where it is ready for commercial use. As soon as we discover precious resources within an asteroid, we will immediately move to phase 3.
Space miners want to move quickly, but to explore and then mine asteroids, a craft will have to land on the surface. Here at Issy-sur-Perrot near Toulouse, Naomi Murdoch studies the interactions between space instrumentation and the surface of celestial bodies.
On an asteroid, we're in low gravity conditions. Things don't necessarily behave in the same way as they do on Earth.
Murdoch is a planetary science researcher. She's taken part in international missions like the InSight mission to Mars. She's also been a consultant for planetary resources.
One of the challenges about interacting with asteroids is that the gravity is not necessarily constant across their surface. So what that means is there might be some regions of the asteroid where you're lighter and other regions where you would be heavier. On some asteroids, there's even the possibility that around the equator, because they're spinning very fast, the centrifugal force actually balances out the gravity. We have evidence that the surface material is moving across the surfaces of these bodies. There are avalanches on these bodies. We're going to need to understand how a spacecraft will interact with the surface. So here at Issy-sur-Perrot, we've taken an existing drop tower that was used for crash tests, and we've rigged it up with a system of pulleys and counterweights. You have a box and you let it fall. Inside that box, we can have small amounts of gravity. So we take a projectile and we let it go. And we're going to have very low velocity collisions in low gravity conditions, very similar to what we're going to have on a small body.
These tests helped prepare the deployment of Mascot, one of 3 small landers sent to the surface of Ryugu. They weigh just a few kilograms and can rebound until they find a stable landing spot. But a mining probe would have to land in a specific location.
So one of the ways that people have thought about landing and attaching to asteroids is to land on the asteroid and really to anchor into the surface. One of the problems with that is that if we are attached only to the surface material itself, that surface material is not attached necessarily to the consolidated material underneath. So if this material starts to lift up, then our spacecraft is also going to lift up. So it's very, very challenging to come up with the perfect solution for how to land on the surface, attach to the surface, and stay there.
There are two choices. Either we wait until we know more about the asteroids and our hypotheses are more accurate, or we send a mission to the asteroid we want to mine to study and understand it. Then we go back later with the tools to mine it. The problem is that the asteroid revolves around the Sun. Just because it's accessible at a given point doesn't mean it will still be 6 months later. We have launch windows, which complicate things, but that would be the ideal way to do it.
There is another idea, borrowed from NASA scientists. Capture an asteroid and bring it back to Earth.
That's extremely complicated. Small asteroids are generally just accumulations of material, like a heap of rocks that are collected only because of their gravitational attraction. Even if it's weak, it's enough to keep them together. They're known as rubble piles. If you want to capture one, you have to slow down its rotation, and they sometimes complete a revolution in less than a minute. You have to control something with very little cohesion that could fall apart. You have to put it in an enormous sack. It's very complicated.
Where we'd be capturing small asteroids in their totality and be returning them into perhaps a lunar orbit. The Moon, fortunately, is in a relatively fixed position compared to the Earth, so by putting an asteroid into a lunar orbit, you essentially create a moon of the Moon, which everybody's quite excited by, and it allows you to be 3 days travel time away from your asteroid mine.
When I talk to companies that want to mine, I don't want to discourage them, but at the same time, I'm a scientist. I want to explain the complexities. So the approach has changed. Instead of bringing the asteroid to Earth and mining here, we concluded that it would make more sense to do it in situ, and then use them as resources to go further, for example, by making fuel, and then seeing if there are other useful elements around.
So long as scientists are interested in further research and exploration, it's hard to get investors excited. In September 2018, Planetary Resources went bankrupt, a €13.7 million write-off for Luxembourg. A few months later, Deep Space Industries was bought by Bradford Space, an international company specialising in the manufacture of space systems. They're interested in developing water-based propulsion for limited use within Earth's orbit. Asteroid mining seems to have been put on hold. There's a missing link between Earth and deep space, between short and long-term thinking. One man understands this well. He's a so-called prophet of new space concepts and a titan of the logistics world. He invests $1 billion a year in space projects.
Let me show you something.
Washington, May 2019.
This is Blue Moon. We've been working on this lander for 3 years. It'll soft land in precise way, 3.6 metric tons onto the lunar surface. It's time to go back to the moon, this time to stay. There are thousands of creative people coming up with new ideas about how to use space. But those entrepreneurial companies cannot exist today. And the reason is the price of admission to do interesting things in space right now is just too high because there's no infrastructure. When we have that infrastructure in place for the future space entrepreneurs, you will see amazing things happen. And one of the things that we have to do is inspire those future generations.
Humans think in very short time scales. Humans think in terms of 10 years as being a long time, 50 years as being a lifetime, and 100 years as being inconceivable. But 100 years is not a long time. If you're talking about the history of an Earth, 100 years is a nanosecond. We can do great things in our lifetime. So when people say you're a dreamer, I would say they're short-sighted.
According to our study, mining resources or water on the Moon would be possible in the next decade. All the other uses that we envisage will develop over the next 40 years or so.
Asteroids aren't science fiction. we go there. We've got spacecraft there at the moment. Look at the NASA spacecraft to Asteroid Bennu, JAXA spacecraft to Ryugu. They're there. What science fiction perhaps is being able to mine them effectively. But using these asteroids as a stepping stone for humanity to get further in the solar system seems like a good way forward.
The future that I would like to see is a future where humanity is cooperating to exploit the resources of the solar system in a way that's sustainable and in a way that allows us to essentially continue to flourish scientifically as a human species, to explore the solar system.
I have no illusions about it. If one day, and I doubt this, there's a real space conquest over resources, it will be survival of the fittest.
So, we get to choose. Do we want stasis and rationing? Or do we want dynamism and growth? We have to use the resources of space. We must have a future for our grandchildren and their grandchildren of dynamism. We cannot let them fall prey to stasis and rationing. What could this future look like? Where would 1 trillion humans live? This would be an incredible civilization. High-speed transport, agricultural areas, no rain, no storms, no earthquakes. Some of them would be more recreational. There'd be whole new kinds of architecture.
It's hard to believe we'll be able to colonize other places, and I wonder if we'll need to. When we go to space, we realize that space is empty, that everything is very, very far away, and that most places are hostile to human life. There's nothing like our own planet. Nothing.
Ultimately, if we don't learn anything, or if we refuse to learn anything, then we're doomed to repeat the same mistakes. Yes, we'll have a little more, and we'll make a few more mistakes. We'll waste a bit more, we'll become more numerous. We don't have unlimited resources on this planet. We have to learn to manage them better, and quickly.